Hello students, Deepak Pandey here, your guide and mentor for GATE 2020 Chemical Engineering. Today's topic is the radiation between grey bodies. If you have gone through the basics of radiation, the bodies are classified into various categories depending upon their radiation properties. So we have black bodies. For black bodies, the value of emissivity is taken as 1. So suppose if there is a black body, then you write that emissivity of the black body is equal to 1, and whenever it's a black body we always use the suffix B, right? Please note that epsilon B is called emissivity, while if you have EB it is called emissive power, but B always stands for black body. But if it is a grey body, so what is the concept behind a grey body? For a grey body, the epsilon value is less than 1, but definitely it's constant over all the wavelengths, right? So grey body is not a real body. Grey body is also an idealized concept. Black body is also an idealized concept. For a grey body, the value of emissivity is independent of the wavelength of the incident radiation, and that is why we also call this as well as black body as an ideal body. So let us discuss that how to solve the problems in GATE examination where the radiation heat transfer is taking place between two grey bodies. So before going into the numerical problems, let us discuss the concepts of the resistances involved in case of radiation. Suppose this is a surface and let us denote this surface as the surface I. For all GATE related problems, you can consider that the surface is opaque. You won't find any problem where there is some transmissivity. So what is the meaning of opaque surface? The value of tau transmissivity is equal to 0. So the value of alpha plus rho must be equal to 1. Now, some amount of incident radiation is falling on this body. Let us denote this as Gi. Fine. Now what is the symbol Gi used for? Gi is used for irradiation. It is called net irradiation falling on the body. Irradiation means whatever radiation is falling on the body must be referred to as irradiation. Now this falling radiation can be emitted or can be reflected, doesn't matter, but the total radiation per unit area, per unit time falling on this surface is called irradiation for this surface. Getting my point? Now because it's a grey body, so its value of absorptivity is not equal to 1. So not all the radiation will be absorbed, right? Some part of this radiation must be reflected. So suppose some part of this is getting reflected, right? So let's say that it's a grey body having emissivity is equal to alpha, right? Emissivity is equal to epsilon and absorptivity is equal to alpha, right? So if Gi is the incident radiation on this body, the part alpha is going to be absorbed, while the part 1 minus alpha of Gi will be reflected. Fine. Also, this body is going to emit some radiation. This is the radiation emitted by the body. Please note that the reflected part and the emitted part, these two are different. So what is the emitted radiation? If it is a black body, then the emitted radiation is EBI. But if it is a non-black body, then what is the relation for epsilon? Epsilon is equal to E divided by EB, right? Emissive power of grey body by emissive power of black body. So for a grey body, the emissive power is equal to epsilon into EB. So I should write this as epsilon, because the name of the surface is surface I, so you can also write epsilon I multiplied by EBI. Fine, right? So please note that the units of Gi, the units of EBI, they are same. Fine. All these terms, the Gi term, the EBI term is having the unit of energy per unit area per unit time. Now the surface is reflecting some radiation as well as the surface is emitting some radiation. If you combine these two together, they are referred to as Ji, and we give this Ji a name. It is called radiosity. So this radiosity term or irradiation term, these terms are also used in GATE examination in mechanical engineering as well as chemical engineering. You should be comfortable with the use of the term irradiation and radiosity. So these two things must be cleared. The irradiation for a surface, it means that whatever radiation is falling on it from all the sources, all types should be included. And the units are energy per unit area per unit time. Radiosity is whatever radiation is leaving the surface. Either it is emitted or it is reflected, both should be considered. Whether it is emitted or reflected, both should be considered, right? So that becomes Ji. Okay. So we can write Ji is equal to 1 minus alpha into Gi plus epsilon I into Ebi. Now this is the equation for radiosity of the surface I. Now if you have gone through the Kirchhoff's law, it says that alpha, the absorptivity of a surface I, let me write this as alpha I, and the emissivity of the surface I can be taken as same, right? So alpha I can be written as 1 minus epsilon I multiplied by Gi plus epsilon I into Ebi. Okay, and that is equal to Ji, right? Fine. So these are the expressions. This is the expression, final expression related to Gi. Let us call this equation as the equation 1. Right. Now, if this is a surface, can you tell me that what is the net amount of heat or net amount of the radiation? Let's call it radiation. Of course, per unit area, per unit time, leaving from the surface I. So let us write that net amount of radiation, leaving surface I. So I am already assuming that the radiation is leaving the surface, the net direction, the net heat transfer is from the surface to the surrounding, okay, leaving the surface I. So how to write it? What is coming and what is leaving? Now I am already assuming that what is leaving the surface is more, and that is why the net radiation is from the surface to the surroundings. So I am already assuming that this is more and this is less. So what is the net radiation? The net radiation must be, let me write this as Qi, right? And that is equal to what is leaving the surface, which is 1 minus epsilon I. I am writing alpha I as epsilon I because these two are same, into Gi plus epsilon I into Ebi. That is what is leaving, and what is coming. What is coming is Gi. Fine. That is the net radiation leaving the surface I. Now use this equation and this equation to write the value of Qi. If you have studied the basics of heat transfer in conduction as well as convection, we always try to write the heat rate in the form of the potential by resistance. So please try to write this Qi by using the two equations in the form of potential by resistance. Okay. So students, this is how you can write the value of radiosity for the surface I. Right. Now, the net radiation leaving this surface, net radiation. What is net radiation? What is coming to it, right? And what is leaving from it. Fine. So I am already assuming that the leaving radiation is more than the radiation which is falling on the surface. So we can say that in a net, the radiation is leaving the surface. Suppose if falling radiation is more and this leaving radiation is less, it means that in a net, the radiation is falling on the surface. So I'm already assuming that this leaving radiation, the emitted plus reflected part, is more than what is falling, and therefore the net effect is the radiation is leaving from the surface. So the net radiation from surface I, so that is Q. Now Q has the unit of energy by time. So let us divide it by the area of the surface I, A. Fine. So now it becomes energy per unit area per unit time. So what is net radiation? Leaving minus falling. What is leaving? Leaving is Ji. And what is falling? Ji minus Gi. Right. Now if you have gone through the previous topics of conduction and convection, we always have a habit of writing, the heat transfer rate or the particular rate of heat per unit area leaving from a particular surface as the potential difference by resistance. So we always have this habit of writing heat transfer as the potential difference by some resistance. Now this is equal to Qi is equal to A multiplied by Ji minus Gi. Now this is the second equation. This equation is first equation. What we have to do from this equation and from this equation, just eliminate Gi. Eliminate Gi. Now that is simple algebra. You can try to eliminate it one or two step. Eliminate Gi, then you are going to get Qi is equal to Ebi. Now this Ebi minus Ji divided by 1 minus epsilon I divided by epsilon I Ai. Right? Now what is Ebi? Ebi is written as sigma. What is Ebi? Ebi is the radiation per unit area per unit time for a black body. And for a black body, the radiation, the emissive power is given as sigma into T raised to the power 4. The absolute temperature raised to the power 4. Now, if you observe this, Ebi minus Ji becomes the driving force, while the denominator of this one is very, very important. This denominator is a resistance. But if you follow this derivation, there is only one surface here, the surface I, there is not another surface. So what type of resistance it is? It is the resistance which is called surface resistance. So whenever there is a gray body, it must have some surface resistance given by 1 minus epsilon I by epsilon I Ai. You just remember this value of surface resistance. Okay, no need to remember complex formulas for various combinations. Suppose for a cylinder, inside a cylinder, for two concentric spheres, no need to remember any formula. Just to remember the resistance, you can write down all the formulas within minutes. Okay, so this is surface resistance for a gray body. Now, if the body is a black body, what is the emissivity of a black body? 1. So what should be the surface resistance of a black body? Do not try to find from here. You may get 1 minus 1. Okay, from here as well. Okay. What is the emissivity of a black body? The emissivity is 1, and therefore the surface resistance of a black body is equal to 0. And for a black body, suppose if it is a black body, then whatever radiation is falling, the complete radiation is absorbed and this part is not there. Therefore, whatever is emitted, that alone contributes to Ji. So I can say that for a black body, this can be a one question that for a black body, Ji is equal to Ebi. Fine. Only for black. Only for black body. Getting my point? Now, this resistance should be considered as a surface resistance for any gray body. Getting my point? Now, whenever there are two gray bodies, each body will be having its own surface resistance. Now, suppose I am considering here a single body. What happens when there are two bodies? So, if there are two bodies, let us consider that case. Now, suppose this is a body having area A1, emissivity epsilon 1, which is not equal to 1, so it's a gray body. Temperature, absolute temperature T1. This is another body having area A2, emissivity epsilon 2 and temperature T2. Fine. Now when you write the resistance here, the first resistance is the surface resistance of the body. Now this should be written as, suppose this one is body 1, so this should be written as J1. And what is the potential here? You should write this as EB1. Fine. For this particular body, you should write EB2, and then there is a surface resistance, and therefore the potential here is J2. Fine. Now in between these two, suppose you want to write the heat transfer, the net heat transfer from body 1 to body 2. Now I'm assuming that T1 is greater than T2. So whenever temperature 1 is greater than the temperature 2, the net radiation is only traveling from this point to this point. It is transferred from body 1 to body 2. Now Q12 can be written as J1 minus J2, right, divided by the space resistance. Now there is one more resistance here. This one is called space resistance and it is given by 1 by A1 F12. Fine. You just remember these formulas or these way of writing the resistances. Fine. So that is called space resistance, and we know that what is F12, the view factor, right? So this is called space resistance. You just remember these resistances, that surface resistance and what is space resistance, then everything is done. Now J1 minus J2 divided by this. Now between these two plates, what are the different types of resistance? The surface resistance of the first plate, space resistance and the surface resistance of the second plate. So suppose if I want to write the net amount of heat transferred, I should write as Q12 is equal to, if you write the driving force EB1 minus EB2, now EB1 is sigma T14, EB2 is sigma T24, divided by sum of all the resistances. So between EB1 and EB2 there are three resistances. Space resistance, that is 1 by 1 minus epsilon 1 divided by epsilon 1 A1, plus this one is surface resistance for the first body, plus 1 by A1 F12 space resistance, plus 1 minus epsilon 2 divided by epsilon 2 A2. Right, this is how you can write the final expression for the heat transfer between these two bodies. Now there are various special cases, and if you use all those special cases, you can get the formulas that you have learned, that you are continuously trying to learn, right, without learning the concept of resistances. So if you know the concept of resistances, no need to learn all those formulas, right? Just to remember the simple space resistance and surface resistance. Suppose, what is the case 1? Case 1 is A1 is equal to A2, fine. Epsilon 1 and epsilon 2, they are not same, suppose, and view factor is equal to 1. Then what is the expression? Q12 becomes equal to EB1, so sigma T14 minus T24, and then you have this area, all the areas are same. So let us suppose that A1 is equal to A2, so either you write A1 or you write A2, so you can write here sigma A1. The area goes into the numerator. What is left? View factor is 1, so 1 by epsilon 1, this becomes minus 1, plus F12 is 1, so plus 1, minus, okay, plus 1 by epsilon 2 minus 1. Now this becomes sigma A1 T14 minus T24 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Now this is the well-known formula that you have learned for heat transfer between two parallel plates, where both the parallel plates are gray bodies. Fine. Now no need to learn all these special formula, just remember the resistances, and it is applicable for any case, for any gray bodies, right? If they are gray bodies, just write the resistances. If it is black, then definitely there is no surface resistance. Fine. Now all these concepts can be applied for other shapes as well. Suppose you have here a sphere, and inside the sphere there is another sphere. Suppose the radiation is taking place like this. You want to write net Q12. Right. Suppose this is body 1, surface 1, and this is surface 2. The surface 1 is having epsilon 1 emissivity and T1 temperature. Surface 2 is having epsilon 2 emissivity and T2 temperature. So how to write the net value Q12? So let me show you here. So how you can write the value Q12? Just write the driving force, that is EB1 minus EB2. Then the resistances. What are the resistances? Surface resistance of the first body, that is 1 minus epsilon 1 by epsilon 1 A1, plus space resistance. Now that is 1 by A1 F12. You can calculate the value of F12. There are various problems in GATE where F12 is asked, right? Then 1 minus epsilon 2 by epsilon 2 A2. Now it can be rearranged in various forms. You can take A1 common, so it becomes sigma A1 T14 minus T24, fine, divided by 1 minus epsilon 1 by epsilon 1 plus A1 goes, so it becomes 1 by F12. If F12 is 1, then you can further simplify the things. Now this becomes A1 by A2 into 1 minus epsilon 2 by epsilon 2. Now just put the values of A1 and A2. This expression is also valid for a cylinder. But what is going to change? The values of A1 and the values of A2, because for cylinder the surface area expression and for sphere the surface area expression is different. The same concept of surface resistances are also applicable in the case of radiation shield, right? Suppose you have a radiation shield. So how to use this concept? You have two plates. Between two plates there is a radiation shield. So for this plate, surface resistance, space resistance, let me draw here. I'm just going to give you the idea behind the radiation shield. You can yourself derive the final expression. Fine. Suppose two plates are there and in between you have a radiation shield. Now in the radiation shield, both the surface are considered. This is an important concept, that this surface as well as this surface is considered, and both of them are having some emissivities. The emissivities of the two surfaces may be same or may be different. It should be provided in the question. Now when you write this, suppose this is at temperature T1 and this is at temperature T2. It may be temperature T3. If required, you can use T3 or not. Having emissivity epsilon 1, fine. Having emissivity epsilon 3 on this side and epsilon 3 dash on this side. And this one is having emissivity of epsilon 2. Suppose area is same, just for simplification. And you can also, okay, let's not take view factor is equal to 1, but let us take at least area to be same. So how to write? Q12. That becomes equal to EB1 minus EB2. Where is EB1? This point EB1, this point EB2. In between, surface resistance, space resistance, surface resistance, surface resistance, space resistance, surface resistance. Fine. All these resistances should be considered. So what is the surface resistance for the first case? Because area is same, so you can multiply this entire expression by area, right? So for the first case, 1 minus epsilon 1 by epsilon 1. What is space resistance? 1 by F13. So F13. Okay, fine. 3 surfaces this plus surface resistance 1 minus epsilon 3 divided by epsilon 3 plus the other side of this radiation shield, that is also going to give you some surface resistance, that is 1 minus epsilon 3 dash divided by epsilon 3 dash plus space resistance, that is 1 by F3 dash 2, fine, plus 1 minus epsilon 2 by epsilon 2. Please note that I am not considering the resistance by conduction, because the radiation shield is considered to be very thin. If it is given that it is also having some conduction resistance, then definitely you have to use here. So this is the expression for radiation shield. Now it can be simplified further for various cases. You can take emissivities to be same, you can take view factors to be unity and area to be same. Then a very simple expression you can get. So you must have learned all those expressions, but these are the concepts behind those expressions. Fine. So this was the explanation that how to understand the radiation between two gray bodies. So I hope the explanation is clear and you can easily utilize the concept of resistances in various problems of radiation in GATE chemical engineering or mechanical engineering. Thank you very much.